first question, we want to draw both chair conformations given the skeletal structure and then identify the conformer that dominates at equilibrium. And for simplicity, I already drew out the empty chairs. Again, as I said in the previous video, I really recommend just memorizing these structures and being able to draw them before you're even given a problem. All right, so here, let's start with this first one. So here we can see that we have one substituent. So the only group that we're going to add in is that hydroxyl group. So we're going to label this carbon right here as carbon 1, and then arbitrarily assign a carbon within this first structure as also being carbon 1. And as I said in my previous video, it doesn't really matter which carbon you choose, as long as everything that comes after it follows along. All right, the next thing we're going to do is take a look at this hydroxyl group. And so we can see that it's wedged. And if we recall, a wedge means that the group is going to be tilted up in the chair structure, and a dash group is going to be tilted down. And so if we are to draw in the two substituents for this carbon number 1, we can see that the one that is axial is pointed up, which means that's where that hydroxyl is going to go. And then that hydrogen is going to be tilted down since it's dashed. And so we're going to add it to that equatorial position, which is slightly tilted down. All right, the next thing we're going to do is draw that chair flip. And so for this, after we do the chair flip, we move everything over 1 carbon clockwise. And so now this carbon down here is carbon 1. And so now we have to add in our group. And for this carbon here, we have 2 potential positions, one pointed down and one kind of tilted a little bit up and to the right in the equatorial position. And so again, we want it to be tilted up. And so our OH is going to go right here, and our hydrogen is going to be in that axial position. And so now to determine which one is the most stable, or the one that dominates at equilibrium, we would want to look at the relative position of that OH. So in this first one, we have an axial positioning, and then in the second one, we have an equatorial positioning, and then everything else is just hydrogens. And so the only thing that we really care about is this OH being in the most stable position where it experiences less strain. And so we want it to be in the equatorial position, which means that this second conformer is going to dominate equilibrium. So when we draw our equilibrium arrows, we'll draw a longer arrow going to the right. And I'll just circle this too, make it more clear. All right, so let's move on to this next one. So here we have multiple different substituents. So let's first choose a carbon to start off with. And I'm just going to start with this bromine. Then we're going to place that in that top right again. And so we're going to have positions at carbons 1, 2, and 4. And so I'll just label those positions on the chair here. And so from here, we can add in the different groups or potential positions to each of those carbons. Then if we take a look at this bromine, we can see that this bromine is dashed. And so dashed means we want it pointed down. And out of the 2 possible positions in carbon 1, we have that this group is tilted down. And so that bromine is going to go there. And the hydrogen that is wedged is going to go up. Next, we have the methyl and the ethyl group on carbon 2. In this one, we can see that the methyl group is dashed and the ethyl group is wedged. And so we want that methyl group to be dashed. So we want it to be, since it's dashed, we want it to be pointed down. And so going down, we would have this methyl group right here. And the one pointed up would be that ethyl group in the equatorial position. All right, lastly, we have carbon 4. So I'll draw on the hydrogen here. In this one, that hydrogen is dashed or pointed down. And so in this chair structure, the one that's pointed down is going to be that bond. And so here we'll add in that hydrogen here and the methyl in this position here. To do the chair flip, we'll next rotate all the carbons over 1 position. So 1, 2, and 4 here. And now we're going to move all these substituents over 1, and we're going to flip whether they're axial or equatorial. So that bromine was initially equatorial, so in this next one is going to be axial. And the hydrogen is going to be equatorial. And again, here you could follow that dashed and wedged rule instead. You don't have to go the flipping route. It's up to you which way is easier. So you can either go through and just flip everything from equatorial to axial and from axial to equatorial, or you can go through and just identify which bond is pointed down and write the correct one corresponding to the wedge and dash. And your answers should line up. So regardless of which way you do it, your answer should give you the same structures. All right, next for carbon 2, we can draw the methyl and the ethyl. So here we're going to have these two bonds here. And so we would want that methyl group to be pointed down. So that's going to go from the axial to the equatorial position. And then the ethyl group will be pointed up. And finally, we have that carbon 4. In this one, we have the methyl group. It initially was equatorial, so here it's going to be axial. That hydrogen is going to be equatorial. And again, we're retaining that shift down. We can see that in all the groups that I highlighted, even though they flipped from axial or equatorial to the other one, they're still pointed down here for all the dash groups in the initial structure. All right, so now we can go through and identify which one's the most stable. So for this, we would want to go through and label each group as axial or equatorial. So in this first one, we have 2 equatorial groups. And here I'm only going to label the non-hydrogens. We don't really care about hydrogens since they're really small, and they're not the ones that are going to lead to that diaxial strain. Do the same thing here. And so what we can see here is that majority of these groups are pretty similar in size. There's not like a really huge group that would lock the chair into one of the given conformers. And so here we just want to assess based off the number of groups in the equatorial position versus the ones that are in the axial position. And so we can see that in the structure on the left, we have 3 groups in the equatorial position, including that bigger ethyl group. And in the structure on the right, we have primarily axial positions here. So you can see that this methyl, ethyl, and bromine are all axial. And so we know that axial is destabilizing. Generally, structures prefer placing their substituents into equatorial positions. And so we know that this one on the left is going to be the dominant one at equilibrium. And so when we draw out those equilibrium arrows, we'll draw a shorter one going to the right and a longer one going to the left. All right, now we can move on to this last one. So same thing as with the others. We're first going to label that first carbon. We can start with the one at the top. And just as a general note, if you choose to choose a different carbon as a starting point, your axial and equatorial positioning might be flipped depending on where you placed carbon 1. And so you may have potentially done this question correctly, but your answer might look slightly different than here. There's a lot of different ways that you can write out the potential answers. And so just don't be discouraged if your answer looks slightly different. It's possible that you did it completely correctly. All right, so here, let's take a look. So here we have this chlorine is wedged. And then we have another wedged hydrogen right here. And the isopropyl group that is dashed. And so based off carbon 1, we know that we have these 2 potential bonds that that chlorine could occupy. And we want the one that is pointed up because that chlorine is dashed. And so that chlorine is going to be in the axial position here, and that hydrogen is going to occupy the equatorial position. Next on carbon 2, we have these 2 potential bonds. And so here we have an isopropyl group, which is dashed. And so dash groups are pointed down. And so the isopropyl group would go in the axial position here, and the hydrogen would be equatorial. Next, we would do that chair flip. So everything would shift over 1 carbon, and we would swap positionings for axial and equatorial. So that chlorine that was initially in the axial position would end up in the equatorial position here. And we can see that it's still tilted slightly up. I highlighted those. highlight those in red really quickly to correspond to the color that I have in the structure on the left. All right, next we can do the isopropyl group. So we can see that isopropyl group was initially in the axial position, and so now we want to move it to the equatorial position. And so our two possible bonds in the structure look like that. And so we'll have the isopropyl in the equatorial and that hydrogen pointed up. And so we can see that both of those isopropyl groups are tilted down in those structures, which corresponds to the dash structure on the left. All right, finally, we want to determine which one is the dominant conformer. And again, we'll go through and label all the groups as axial or equatorial. And we can see that we have two axial groups in that first structure and two equatorial ones in the second. And so this is going to favor the right side. One other note about this question is that this isopropyl group is very steric, like it's very big. So there's a lot of steric hindrance that comes with it being on a ring. And so the equilibrium will strongly favor this side, the right side, where it places that isopropyl group into the equatorial position. And so while for something like the second one, we might see less of a favoring of that left side at equilibrium, that isopropyl group heavily favors that right side. All right, so we're done with that question. So this last question for this problem set is to convert each of the following chair conformers to a skeletal structure. And so for this, we can see that we're given the chair conformation and we have to draw out the skeletal structure. So the first thing we're going to do is draw that six-membered ring for all of these. So since we're working with chair conformers that have 6 carbons, we know that all of these are going to be cyclohexane structures. Next, we're going to take a look at each of the positioning. So we can see that this chlorine right here is tilted down. And for all of these, I'm going to choose that top right carbon as carbon number 1, just so we're staying consistent with how we're choosing. Again, it doesn't really matter which one you choose as long as you're keeping track of them as you go around the ring. All right, so here we have this chlorine is pointed down, and so down means dashed. So we have a dashed chlorine on carbon 1. In the second one, however, we have a chlorine that's tilted slightly up, and so up means wedged. And so on the second carbon over, we're going to have a wedged chlorine. All right, so that's done with that first one. Next, we can take a look at this second structure. In here, we have substituents on carbons 4, 5, and 6. And so first, I'll highlight all the ones that are tilted down, which happens to be all 3 of these on this structure. And so for carbons 4, 5, and 6, we can draw in all those groups wedged. So we'll have a wedged bromine here, another wedged bromine on carbon 5, and then a wedged methyl group on carbon 6. And that one was pretty straightforward because all those groups are tilted up. And again, just as a reminder, we're not looking at whether it's axial or equatorial. We're just looking to see if the line is tilted slightly up at all. All right, next one, we can take a look here. So we have this group is tilted up, and then this tert-butyl group is tilted up here. And so we can draw in that methyl group on carbon 1, and then that tert-butyl on carbon 4. And then next we can add in those 2 groups that are tilted down, which is that OH and that methyl group on carbons 1 and 6. On the top one, and that methyl group is 1 over on carbon 6. All right, and note that we can see that in the structure on the left here, that tert-butyl is so big that it locks that conformer into the equilibrium structure, into that equilibrium state where it's placed into the equatorial position. Uh, the other chair conformer for this structure would not be present in a high percentage within a given system due to that tert-butyl. All right, so that wraps up this video. If you haven't already, I recommend going through those, the PDF of the notes and listening through those.